Okay, so here we're going to continue our conversation on vectors. We're going to talk about vector multiplication. In the last one we did vector addition. Here we have two rules for vector multiplication, and they're important because they tell us different things, and they're used in different applications. The first one we're going to cover is called the dot product. The dot product is most principally used to compute the angle between two vectors. There's a lot of value in knowing this number. Right now we're not going to go into what that value is. We're going to go into the methodology. So for the dot product, we have to understand the first formulation of the equation, which you can see here on the right. If I have two vectors similar to the lower left, then A dot B equals the magnitude of A times the magnitude of B times the cosine of the angle in between. However, if we most principally use this to compute the angle between two vectors, then we have to have an alternative formulation, because A dot B, or theta, is foreign to us. So the alternative formulation for 2D is this: the x component of A multiplied by the x component of B plus the the y component of A multiplied by the y component of B. This is the summation of the piecewise products. That's what this is called. This is for 2D. For 3D, we have AX bx plus ay by, and following suit with the name, the summation of the piecewise products, we have az times bz. This is for 3D. We could keep going. Ax bx plus ay by, oops, I didn't put a y there, plus az bz plus at times bt. This is for 4D. So we just keep going. However, let's just use our 2D case here, and let's look at or examine how would we compute theta. Well, we have to first know that if we have a two-dimensional vector A, that A's magnitude is equal to the square root of the sum of the squares, ax squared plus ay squared. And if I have a 2D vector B, the magnitude of B is equal to bx squared plus by squared. This is the square root of the sum of the squares. So now I can formulate this value, and if this formulation equals the left-hand side of the first equation, then I now have all of the requisite information to solve for theta, because I have that A dot B equals ax bx plus ay by, that equals the magnitude of A, which is again the square root of ax squared plus ay squared. We'll put that in parentheses, multiplied by the square root of bx squared plus by squared times the cosine of theta. Well, now I can reorganize and I can say, okay, let me adjust, and I really don't like how all of that's slammed together. So there we go. And we can say that in the end, we have that theta, well, we'll do it piece by piece. The cosine of theta equals, again, the magnitude of A, ax squared plus ay squared. The magnitude of B, the square root of, sorry, I didn't say that before, the square root of bx squared plus by squared. All of that. Oops, that's my denominator. I apologize. You know what? We're going to cut down time. We're going to call that the magnitude of A. So here I have ax bx plus ay by over the magnitude of A times the magnitude of B. And then we have that theta equals the inverse cosine of that entire thing, ax bx plus ay by, all over the magnitude of A times the magnitude of B. There we go. That's how we compute theta. If we're looking for the dot product, we just use these formulations. And we also understand that this nets a scalar value. And that's important because we're feeding it vector values. So we feed in things that have a magnitude and a direction, or an x, a y, an x, a y, a z, or an x, y, z, t, or however many dimensions we have. And what comes out is a single number, which only has a magnitude. Now, the corollary of this form of multiplication is called the cross product. And for the cross product, we have to start with a very simple example. You see, the cross product is used to compute a vector that is orthogonal to two vectors. Now, orthogonal means what? It means perpendicular. It means that if I compute the cross product of two vectors, then I have a third vector that forms a 90-degree angle with both vectors. So here's V1, here's V2, here's V3. And what I have is that V3 equals V1 cross V2. And it means that V3 is orthogonal or perpendicular or at a right angle to V1 and V2. Now the simple example is this, and it's very difficult to describe without going through the hand motions as we would in class, but suffice it to say if we were changing a tire, we'd use a T-bar tire iron similar to the one you see in front of you. The T-bar tire iron would fit onto a lug, and then out of the lug extends one rod, and then as it is a T, two arms protrude at 90-degree angles away from that. You grab the ends of those arms and you push up with one hand and down with the other in a counterclockwise motion to loosen the lug nut. The force you're exerting is actually, if we pretend that the T-bar starts straight across even with the horizon, you push up with your right hand and down with your left hand. The distance from the force that you're exerting on the bar to the line of action, which is the bar that extends all the way from the lug nut back to where your T-bar is conjoined at the T's, that's the distance. And if we take F cross D, we get a torque. We get a spinning. So the way to think about this is this. You're putting a bar on something that rotates. You're pushing up and down, and you're getting a rotation about a line. So F cross D, the force cross the distance, gets a torque, and the torque is that rotation. The rotation happens on a line that is 90 degrees right here. Let's see if I can do it. There we go. Sorry, that's your T-bar arms. It is, here, if I were to continue my force up, 90 degrees, and here, if I were to continue my distance over, 90 degrees. My distance just traverses along my arm. That's why I put the first 90-degree angle there. But I have a line of action, that green line, right here, okay, that is at a 90-degree angle from my force and a 90-degree angle from my distance. Now, to compute a cross product, we have to do several things. The initial formulation is that we'll say V1 cross V2 equals the magnitude of V1 times the magnitude of V2 times the sine of the angle in between. Now, usually we don't have enough information to get through this, so we could do the dot product, compute it, but we could just do this. Okay? That A cross B looks like this, and we're going to focus on this top. We compute it, or we assemble an array. In the first row, we have the vector components I, J, and K. In the second row, we have the X component of the first vector, the Y component of the second vector, and the Z component of the X component of the first, the Y component of the first, and the Z component of the first. In the third row, we have the X component of the second, then the Y component of the second, then the Z component of the second. So to put numbers to this, we do the following. Let's pretend we have two vectors, C and E. C is 4i plus 7j minus 9k. That means that this is the X component, this is the Y component, this is the Z component. That's what the I, J, and K mean. So I have E similarly. I would like to find C cross E, so over here in my solution I've assembled an array. Now, please notice that when we assembled the array, we had straight lines. Oops, sorry, my computer's lagging a little bit. Those straight lines mean we're going to compute the determinant of this matrix. So A cross B actually equals the determinant of that matrix that we assembled. So I have IJK. I'm using the diagonal method here, so I'm rewriting all columns except the last. I have 3 diagonals that are down and to the right, 3 diagonals that are down and to the left. I've assembled them sort of out of orders to keep my I's, my J's, and my K components together, and then I did nothing more than collect my terms. So I distributed this out, added together my I components, my 2, added together my J, and added together my K. This is how we compute the cross product of two vectors. And also remember that once we've done that, what we now have is a vector right here. We'll call it, I guess, D. D, which if we were to draw in 3-dimensional space, is 90 degrees from E and 90 degrees from C. So this is the second form of vector multiplication. So there we go.